Welcome to Cookie's Maths and Science Hub. Today we're going to be exploring the topic of titrations. So, what is a titration? A titration is just a fancy word for a volumetric analysis. Now that might sound fancy as well, but all it means is an analysis between two solutions, hence volume, remembering we measure solutions in volume. It's a widely used quantitative analytical method, meaning it's based around numerical values and precise and accurate measurements. Titrations allow us to determine the concentrations of unknown solutions by using a known solution. Effectively, we can take a known solution with a known concentration and a known volume, which we call a titrant, and add it to a known volume of an unknown concentration, known as a titrand, to determine the unknown concentration of that solution. This is a fantastic technique with many different applications. We'll go through the four main types of titrations now. By far the most common titration, and the titration that serves as an introduction for most into the science behind titrations and volumetric analysis, is acid-base titrations. These are titrations between, well, you guessed it, an acid solution and a base solution. It involves the titration of an acid with a base, or vice versa, resulting in the formation of water and a salt, effectively what we call a neutralization reaction. When an acid and base react, they produce a water and a salt. We can use this reaction to determine the unknown concentration of one or the other. The equivalence point, that is, the point where they have fully reacted with one another, is when we have a neutral solution. Now, how do we tell this equivalence point? Well, in acid-base titrations, we use what's called indicators. pH indicators to be exact. Now, pH is simply a scale of how acidic something is. And we'll go into more detail about the pH scale in another video. The most common titration indicator is phenolphthalein and used very often in early labs into titrations, which goes a light pinkish to darkish pink as you become more basic, as you can see on the scale on the right. So when performing an acid-base titration using phenolphthalein, you want that really light pink to move back to the clear. As you can see, 7, which is our neutral on our pH scale, is still clear. So we want it to be just before that point of light pink to indicate a full reaction between our acid and a base. Redox titrations are a little more complicated and won't be explored until you get into the higher grades of around 11-12 chemistry. Redox titrations involve a chemical reaction where electrons are transferred between reactants. This involves titrating a reducing agent with an oxidizing agent, or vice versa, depending on what you're trying to determine. Indicators can be used in this case, but aren't often needed for a lot of reactions, as there is often a distinct color change, as given in the example on the right. As you add potassium permanganate to oxalic acid, you'll get that color change to that light pink when you reach that end point, or that equivalence point. You can also use changes in voltage, as transfer of electrons involves the change in voltage. So you can use potentiometric means to measure that endpoint. Precipitation titrations involve, as the names start to suggest as you can see, precipitation reactions, and involves the titration of a soluble reactant with a solution containing a precipitating agent, leading to the formation of an insoluble, or in this case, a solid product. These endpoints are quite easy to detect, as it usually results in the formation of a solid. Given our example on the right, you can see a solid has clearly formed, and that way we can easily tell the endpoint, or that point just past the equivalence point, when this reaction has fully taken place. They are used less than our other titrations, but often applied in the analysis of specific ions, when looking for specific ions within solutions. Now, sometimes that exact precipitate doesn't take a while, doesn't exactly form fully and isn't fully clear, in which case we refer to a sudden change in turbidity as an endpoint. Turbidity simply being how clear a liquid is, or the relative clarity of a liquid. Definitely the most complex of the titrations is complexiometric titrations. Again, it's pretty clear in the name. These involve the formation of a complex between a titrant and an analyte, often utilizing chelating agents, which are simply compounds that can form multiple bonds with a single metal ion. That's a lot of big words, and realistically we're only going to cover this one briefly so you have a general idea of it, but you won't explore this until you're well into your chemistry years at university. These are frequently employed for the titration of metal ions, especially those forming stable complexes. Now, the endpoint detection can be used indicators for specific metal ions, but often make the use of instruments for precise detection, such as different electrodes or detectors within the solution itself, as is given in the diagram on the right. For those of you who are exploring titrations for the first time, it can also be the first time you explore some different equipment within the lab. Now, hopefully by this point you're familiar with your beakers and different sizes and shapes and all that sort of stuff, but there are three key parts that we use for most people for the first time during a titration. This is the burette, which is a large glass cylinder on a retort stand that can be used to deliver precise amounts of liquid. A pipette, which is a very accurate way of measuring a solute. And a volumetric flask, which is used for turning solids into liquids with precise amounts. This allows us to determine concentrations, which can be very helpful in titrations when we're trying to be accurate with exactly what we're trying to find out. Make sure you're familiar with these as you move forward into your titration studies, as you'll use them lots and lots and lots and lots and lots throughout all your titration labs, as well as many other labs you'll start to encounter as you head into those years of college. As we shift our focus now into how we prepare for titrations and the calculations involved, there are two important formulas we need to know. All of these have to do with moles. If you're unfamiliar with moles, I suggest you check out my video on moles, so you're a bit more familiar with that concept, as they play an important role in titrations. Now, the number of moles can be equal to a couple of different things, and we need to know all of them when calculating titrations, as we use both solids and liquids. Our formula on the left is more so for our solids. We know that the number of moles, which is N, is equal to our mass in grams over our molar mass, which is simply the mass per mole. This allows us to use solids when calculating our titrations, as we can make our solids into solutions, which we'll talk about in a moment. Our formula on the right is more so for our solutions that we already have, and we know that our number of moles is equal to our concentration in moles per litre, multiplied by our volume, which is in litres. That's an important thing to remember. Although you'll work with small quantities in titrations and other chemical formulas, you need to remember we use all formulas with litres, meaning you'll need to divide by 1,000 or convert in other means that you know, such as times 10 to the negative 3 or anything like that, to make sure any millilitres or any other unit of measurement becomes litres. Oftentimes in titrations, you'll have to prepare a solution from a solid. This is a common technique used in many different analytical techniques within science. However, titrations are probably the first time you'll encounter it. We begin by weighing the solid, and you do that using an accurate measurement such as scales or anything like that. And you need to sometimes calculate the required amount of the solid substance. You then dissolve in a relative solvent. Now, most times in titrations, you'll just be using deionized water for your solvent. You just need to mix it up in a beaker and make sure it's fully dissolved. Now, because we deal with exact amounts within titrations, we have to then transfer this solution, however much we've made up, into a volumetric flask of a relevant amount. If you need 100 mils, then you'll use a 100 ml volumetric flask, 250 mils, 250 ml volumetric flask, etc., etc. Now, you need to make sure you're careful when you transfer it from one beaker to another that you've rinsed out your solution thoroughly, as you don't want to leave any solid matter behind. Because this is quantitative, meaning it's all numerically based, anything you leave behind can affect your calculations. Then you simply fill up to the mask of your volumetric flask, give it a bit of a shake, and then you've turned it fully into a prepared solution. However, obviously, like I said, sometimes you'll need to do a few calculations in this process. So let's look at an experiment now and an example for this experiment. For an experiment, 100 mils of 2 moles per litre of NaOH, sodium hydroxide, is required. How much solid is needed? Well, we know that we can find the number of moles in two ways, both in a solution and from solids. Given that we have a solution as our final requirement, we can use that initially to find our number of moles. So our number of moles is equal to our concentration times volume, which is equal to 2, which is our 2 moles per litre, times 0.1. You'll notice I've converted the 100 mils into litres, which simply gives us 0.2 moles. Now we're trying to find how much mass we need, so let's look at our other equation now. N is equal to mass over molar mass. Rearranging that, bringing the molar mass across, we can find that mass, or just our lowercase m, is equal to n times our uppercase m, or our number of moles times our molar mass. Now, once more, I suggest you check out our moles and molar mass video that will go into how to find the molar mass, but these numbers can be taken off the periodic table of the relative atomic masses for these calculations. So our mass is then going to be equal to 0.2 times 22.99 plus 16 plus 1.008, with the 22.99 being our sodium, the 16 being our oxygen, and the 1.008 being our hydrogen. Putting that into your calculator, because we don't expect you to do these things in your head, you'll get your mass is equal to 8 grams. Therefore, we must weigh and dissolve 8 grams in a 100 ml volumetric flask for the desired amount and concentration for this experiment. You can see that the calculations aren't difficult, and the process is very straightforward. You're pretty much just dissolving the solid in a liquid and then putting it in your volumetric flask and making up to the mark. But you need to make sure you're precise in any of these steps, as any issues or any errors can cause issues in your later calculations. Now, calculations for finding the unknown concentration can get quite complex, and I suggest you check out our molar ratio calculation video to see how different ways that you can calculate when you have imprecise ratios between reactants within a chemical equation. However, for this case, and for some basic calculations, and for your introduction to titrations, you'll often use a straightforward formula with straightforward chemicals. In these such titrations, there is a 1-to-1 ratio of the moles present of a reactant. This allows us to make use of the formula C1 times V1 equals C2 times V2, where C1 and V1 are the known solution, and C2, V2 are the unknown solutions. More complex equations, like I said, require the use of molar ratios to solve, and that's something you'll explore throughout your years as you progress further into your chemistry studies. Let's look at an example now. So, using that standard solution that we just made up, we're going to use 31 mils of that solution, our sodium hydroxide 2 moles per litre solution, to reach the equivalence point with 20 mils of hydrochloric acid solution, HCl, of an unknown concentration. And we're asked to calculate what is its concentration from that experimental results. So, using our C1 times V1 equals C2 times V2, what do we know in this case? Well, we know our C1 and V1 because we use 31 mils of 2 moles per litre NaOH. So that's our C1, 2 moles per litre, and our V1, 31 mils. And on the right-hand side, we don't know our C2 because that's what we're trying to find, but we do know our V2 because we had that 20 mils of HCl present. Rearranging the formula, you can see that we have C1 times V1 over V2 equals C2. This gives us C2 is equal to 2 times 0.031. Remembering, we have to convert back to that litres, so you just divide that 31 by 1,000, over 0.02. Again, same thing, 20 mils becomes 0.02 litres. Punching that into your calculator again, C2 equals 3.1 moles per litre. Therefore, through titration and through our calculations, we have determined the acid to have a concentration of 3.1 moles per litre. This is a pretty standard acid-base titration as this first example. Thanks for watching. Hopefully now you have a really good idea of the basics of titrations, how to conduct one, and some of the equipment and calculations involved in the process. We hope to see you soon. Please be sure to like, share, and subscribe this video.